So we'll start with a new topic today. So, as I briefly described yesterday, right, in the last lecture, that in all of the problems that we discussed by now, we always assume that we are given a fixed one-step transition probability matrix, and we did not have any control over it. But in certain problems, you will have actually an opportunity to choose one action from a set of possible actions, and the effect of that is going to be like actually changing this one-step transition probabilities with which the process goes forward. And if possible, right, then you will try to find the best actions that will perhaps permit you to avoid some undesirable states in the future. But in general, we will have a cost to minimize, and perhaps, or at least in this class, we will be looking at the problem of finding actions that will minimize the long-run expected average cost. Right? And the actions, for example, could be in the form of just replacing a machine or repairing a machine. It could be a minimal repair, it could be a major repair. If you just think it's a problem of machine maintenance that we discussed actually last time. So I am actually start with an example of that kind, first to give you an idea about what sort of problems we will be looking at in the next 3 hours. And then we'll start discussing how to formulate it and how to solve it later. Okay? Okay. So this is, okay, so the title is going to be Markov decision processes. Okay. Right. And we will start with an example, a sample problem, a maintenance problem. Now we are interested in finding the optimal maintenance policy for the problem that I'm going to describe right now. Right? So suppose that we are concerned about a machine which is key for the production, and the machine is being, since it is important for the production, it is being inspected every week. Okay? So we have a machine which is inspected, right, every week. At the end of every week or at the beginning of the week, I guess it makes more sense to just check the status of the machine at the end of the week. So if there is anything that you have to do about it, you can plan accordingly before the next week comes in. Right? Okay. And every time you inspect the machine, then you will also find out the status of this machine. Right? Machine can be in one of 4 possible states. Machine can be in one of the following, okay, following 4 states. We'll label them first of all by 0, 1, 2, and 3, right? So these are states. Just to give the concrete meaning to these things, let me describe quickly what they mean. Okay, so this is the description. 0 means the machine is in good as new state, right? Good as new, right? And 1 is, if the machine is in state 1, it means that the machine is operable, okay, with minor deterioration. Okay. If it is in state 2, that's more serious than state 1. It is still operable, but with major deterioration. Okay. The implications of these things in terms of the production, if it is the machine is has minor deterioration, the fraction of defective production is going to be relatively low. So it is not going to be zero. Let's say if it is good as new, then the production, the percentage of defective items is going to be zero. Here it is going to be positive, but when it is, it has a major deterioration, then the percentage of defective items in the production is going to be relatively high, right? If you compare it with state 0. And if it is in state, if the machine is in state 3, that means that the machine is inoperable, okay? Or in other words, its production is unacceptable. Right? Unacceptable output quality. Okay. So these are the possible states the machine that you can find the machine after you inspect it at the end of every week. Okay. And then let's denote by xn. Okay, the state or the condition of the machine. Okay, at the end of week n. Right. And let us suppose that the process X, right, is a Markov chain. Right? And suppose that we also conducted a statistical analysis of past data and found out that the one-step transition matrix, or, well, found out what the one-step transition probabilities are. Rather than giving the matrix, let me describe everything on the state diagram, state transition diagram. I guess on such a diagram it is easier to grasp the information given at once. So we know what states the machine can be. So there are 4 states, right? And if the machine is in state 0, if it is good as new, in 1 week it can go in to any one of the remaining states. When it is going to leave this state with probability 1, right? And by the end of week 1, it already deteriorates, but the level of deterioration depends, well, depends on these probabilities. Okay. So it may be, the deterioration can be minor or major or unacceptable, right? And the probabilities associated with this is 7/8, this is 1/16, this is 1/16, okay? And if you find machine in state 1, in next week you may still find it in the same state with probability 3/4, or may move to state 2. This condition can deteriorate further, right, with probability 1/8, or the condition may become actually unacceptable with probability 1/8. Right? If it is already in state 2 with probability 1/2, it is going to stay there, or with probability another half, right? It's going to move to state 3, right? If machine is in state 3, so it is not in working condition, it stays there until you take an action, right? We have such a situation, right? And then we can also, let me write P based on this information, right? There are 4 states, 0, 1, 2, 3. From any one of these, in 1 step you can go any other state, right? And if you just fill in this matrix, you get 7/8 for this transition, 1/16, 1/16. And from 1 you can go to any one of these states with probabilities 3/4. It can come back to itself, or goes to state 2, 1 with probabilities stage 2 or 3 with probability is 1/8, right? And from 2, okay, you can stay in state 2 or move to state 3 with half probabilities. And if the machine is already in state 3, it is going to stay there with probability 1, right? Now, if the machine is in state 3, right? So we cannot leave the machine in this state is because the production has to go forward, right? So we have to replace the machine. We'll replace the machine with a new one. So next week the machine is going to be, and then you will have a new machine in state 0. Right? So that's the minimum maintenance that you have to make, right? So if the machine, right, is in state 3, we replace it, right, with a brand new one. Okay. And the cost, of course, associated with it is going to be important for us. Okay. And the cost of replacement, namely the cost of a new machine, right, is, let's say, $4,000. Okay. And the replacement takes, okay, we also know that the replacement takes a week, during which you will lose the production because the machine is, we don't have a machine yet to continue with production. Therefore, we will also lose the value of the production for 1 week. That's also a cost associated with replacement. Whenever you decide to replace the machine, right? Here we must. I will say soon that even if the machine is working condition, you may find it appropriate to replace the machine. In that case, you know that you will lose the production anyway. So we have to take that into account as well. So the replacement takes a week, right, and costs, right, a week's production. Let's say this is of value $2,000. Okay. And therefore the total, right? So this is actually together. Let me just continue with the same bullet. So the total replacement cost right? Therefore equals what? 2,000 plus 4,000. It is okay, 6,000 or the 6K, $6,000 or 6K. Okay. Okay. Now this is one thing that we can do, right? We should do, but this is not the only cost that is involved with this problem, right? Even if the machine is operable, right? Since it has some level of deterioration, it is producing this defective items, and they are also going to cost us. Right? So you cannot label either cause customer inconvenience, dissatisfaction, or maybe they are just completely unusable. So you cannot just sell them. So that, but since you actually spend money on the raw materials, right? So that's also a cost to you. So here now we summarize the cost of replacement for each of these states. In each of these states, we will also have production costs, mainly because of production of defective items. Right? Let us summarize them as well. Okay. So there is also the cost of production of defective items in the other three states. It is going to be 0 in state 0 because machine is still in good shape. So that's still actually not realistic, but let's say it is too small to that we can ignore, right? The cost of production of defective items. Okay, so it is going to be $0 in state 0, and it is going to be 1K, right? And state 1 and $3,000 in state 2. Okay? Alright. So I guess we now have all the cost figures for this problem. So one maintenance policy that comes to mind, right? One maintenance policy that comes to mind, right, is just to replace the machine if it fails, right, namely if it is already in state 3, and do nothing, right, to do nothing otherwise, right? Okay. Well, in that case, we already know what the costs are. We have to just look at what the transition properties are, right? In order to figure out, of course, the quantity that we are interested in is going to be, right? So it's going to be what the long run, right? Expected average maintenance cost per unit time, if it exists, of course, per unit time, right? Okay. To check whether this really makes sense, in this case, we have to look at what the corresponding Markov chain. Does it have? Is it ever going to be in equilibrium, right? If only when the states are visited infinitely often, you can talk about long-run expected average costs and so on and so forth. If you leave the state without ever coming back in the future, then this is basically zero anyway. Or maybe it is infinity, actually. In this case, cost cannot be zero. If it is coming from a real application, you expected it, then probably the cost will actually explode. That's even more dangerous. So, what is the corresponding Markov chain in this case? Right? And so, when you say that you actually follow such a control policy, you are implicitly forcing the probability, once the transition probabilities, to take certain values, right? So this was the shape of the system when you don't take any actions, and under this policy, the only change is going to be what? Instead of staying in state 3, every time you find the machine in the state, you just actually move quickly to state 0. That's basically the only difference between the probability, once the transition probability is under policy of taking no actions, and under the policy of taking perhaps minimal action. Maybe just you replace it and just you let the system otherwise, right? So we can just say that under this policy, right, there's a process that keeps track of the state of the machine is still a Markov chain, right? But with new once the transition probabilities, or let's again look at the state transition diagram, right? As I just said, well, of course the states are not going to change, all right? And then you have brand new machine can deteriorate at any level in one period with probabilities 7, 8, 116, 116. If it has minor deterioration, it is going to stay like that with probability 3/4, or deterioration will get worse with probability 1/8, or the machine can even get inoperable with another with probability 1/8, right? If the system or the machine is already in state 2, it stays there with probability 1/2, because we don't take any action. We said we are not going to do anything about the status of the machine, the condition of machine, unless it is already in state 3, right? So these transition probabilities do not change, but now instead of having an arc that comes back to state 3, if you are already there, with probability 1, you move to state 1. That's the only difference, right? Now you look at this, then you ask to yourselves whether this is a regular Markov chain. Is it? Is it? Yes, because? Huh? Irreducible because you take any two states, you know that there is an arc going from one to another, and it is aperiodic because you know, well, there are at least actually, but there is at least one, right? States for which you can actually come back to that one in one state. So this is, we know now that the X under this policy, right, is regular, right? Was this Markov chain regular? Huh? Is it? Is it irreducible? Suppose you started in state 3. Can you go to state 2? You cannot. So this is not actually irreducible. Right? There is one observing state. Every one of them are what we call a transient state. Transient in the sense that after you spend some finite amount of time, you leave the state without ever coming back. Right? So if you want to calculate stationary probability distribution for this one, I mean, intuitively you can give numbers, right? The fraction of time you spent in the long run in state 0, 1, and 2 are going to be what? 0 in the long run, because eventually you will get to state 3. You know that you don't, there is not a machine designed yet that can work forever without really failing, right? So we don't have such a thing, such a miracle yet, right? So eventually, right, no matter at what, in what state the machine could be, right, eventually it is going to get absorbed to 3, and if you don't take any actions, it is going to stay like that. So actually the fraction of time this Markov chain in the long run, right, spends time in state 0 equals 0, in state 1 equals 0, in state 2 equals 0, in state 3, 1. In the long run, if you wait long enough, you know that the eventual process will hit 0, right? But the theorem is not going to work, even though we know what stationary probability distribution you should assign. There is another theorem actually that still covers this case, but we did not discuss that because, well, by just looking at this thing, you can immediately find out what the stationary or the fraction of time the system is going to spend in simple cases. It is non-trivial to find such things for such chains where the states are communicating with each other, right? They are communicating with each other. Okay, so we have to be careful, right? Okay. All right. So this is regular. Therefore, we know that it has a unique, right? Stationary distribution has unique stationary distribution, which can be found which we can find by solving the usual set of equations, right? And we can quickly write them down as well. What are they? So for each of these states, right, starting with 0, right, you ask to yourselves, right, okay, this is what the fraction of mass that leaves state 0. This should equal the fraction of mass that comes in state 0. And what are they? You can count 0 from, you cannot count from 1. You cannot count from 2. You cannot, well, you can, right? In this case, you can count to state 0 from 3, right? And then, well, okay, the fraction of material in state 3 equals 1, and 100% of it is going to move to state 0, so times 1. We have that. This is mass leaving state 1, and you can get state 1 only from immediately, well, only from 0. So whatever is sitting in state 0, only 7/8 fraction of it is going to move to state 1. Right? It is not only 0, but also 1 itself. So we have to be careful about that. So it's the pi 1 times, what fraction comes back? 3/4, right? The remaining 1/4 will just leave without coming immediately back, at least. Some of them eventually comes back, but that's another story. For state 2, right? So you can reach to from, well, even 0, right? So this is pi 0 times 116 plus, you can reach in one step from state 1, and only 1/8 fraction of the mass in state 1 will move forward to state 2, and if you already have pi 2 fraction of the material, and the half of it is going to just return immediately to state 2, right? For pi 3, right? So that's the fraction of material leaving state 3. What is it coming in one step? So you can reach here from 0, 1, or 2. All states actually count in. From here you get only 1/16 fraction. From 1 only 1/8 fraction of whatever is sitting here. And from state 2, only 1/2, right? Half of whatever is sitting in state 2 is going to move to state 3, right? Finally, we know that the total amount of material that moves inside the system cannot escape from the system, right? So the preservation of the entire the mass inside the system. Therefore, we should have this equality, and of course, we are looking for a non-negative solution, because after all, this is supposed to be a probability distribution on the set consisting of 0, 1, and 2, and 3, right? We have this. We can solve these equations. We know that actually, well, has unique stationary distribution, which we can find by solving this, I would just say, but maybe perhaps we should be even more precise, which is the unique, right, solution of this system of equations and inequalities, right? Non-negativity condition is also over there. And when you solve these equations, you find pi 0 to be 2/13, pi 1 7/13, okay, pi 2 2/13, and pi 3, I guess it is also 2/13. You can verify yourselves if you like. And then, right, so we were interested in the long run expected average maintenance cost per unit time, right? This thing equals, now that I know that the stationary probability distribution exists for this one, this is given by what? Since the chain spends pi 0 fraction of its time in state 0 in the long run, and well, being every time we are in this state, we know that it doesn't cost at all, no maintenance or replacement cost. So actually, I wouldn't write that, but anyway, if the machine ever gets into state 1, then there is a cost of producing defective items, which we set it's a cost of $1,000 per week, and which is the unit of time here, right? So we can just, let's write everything in terms of $1,000, right? So this is like the 1K times pi 1. And every time the machine gets in state 2, then I guess the production cost is 3Ks. And this $3,000 is being paid pi 2 fraction of the time, because pi 2 fraction of the time the machine is going to be, right, in the state. And finally, when the chain gets into state 3, then we have to replace the machine and pay for the lost production. The sum was 6,000, right? 4 plus 2. So this gives us the long run expected average maintenance cost, if you prefer to just use this particular maintenance policy, right? And what does this give to us? You just plug all these numbers, at the end you get 25/13K, okay? $1,000, and Okay, we'll see what this exactly means when we start comparing with others. Right? So, okay, is this good or bad? Well, this is probably not the only maintenance policy that you can think of. What we should do, right, is since we are engineers, right, so we are supposed to come up with the best design for the system, right, if among all feasible, possible maintenance policies, of course. We'll just think whether there are other maintenance policies that we should actually consider and compare with this cost figure, right? So we will do that now, right? This is one of them. And the other things, the other possibilities, right, start actually with a minimum repair. The possibility of actually minimally repairing the machine, especially in state 2. Okay? Okay. Actually, there are other possibilities as well. So, as I said, there we decide to replace the machine only if it fails. But last time we also saw an example, like in an age replacement policy, even if the machine hasn't failed yet, that it might be profitable to replace it before it fails, right? And for example, in state 2, you may think that actually these 3,000, right, cost of producing defective items is too high. Perhaps it's also a good idea to just replace it and actually get rid of this state and start with 0 all the time. That's one possibility. Is this a good maintenance policy? How do I know that? I might just calculate the long run expected average maintenance cost for that particular maintenance policy and compare it with this figure to see which one is going to give us the smaller one, right? That's but just one possibility. What else? So I know that in principle I can replace machine before it fails, right? And the other alternative is going to be just overhauling the machine before while it is still in working condition, right? Okay. So let me first list all these other possibilities, and then we will talk about how we can actually evaluate all these possibilities and then choose the best out of all alternatives. Other possibilities, right? We can replace, right, the machine or a machine, because we keep doing this, right? Every time we replace a machine, then we'll of course start with another one. And just production should actually continue, right? We have to just continue maintaining machines even after we replace them. Replace a machine before it fails, right? Or we can overhaul. I change some of the parts. If not the entire machine, we can still actually change some parts inside it, change worn out tools, cutting tools for example. Maybe the rotor is still working, but some of the parts are actually worn faster than the others. Rather than changing the entire machine, you can just actually change parts which you think actually were worn. That will also do some good to this production system, right? We can overhaul a machine, so the cost for this one is given as $2,000, right? And unfortunately, this option is infeasible in state 3. In state 3, if the machine is already inoperable, there is no way to just bring it back online unless you replace it with a new one, all right? So it's impossible, or maybe it's really economically infeasible to really repair a machine which is already inoperable. Okay? And we also know that this option does not improve the condition of the machine if it is in state 0 or 1. If the machine is in state 0, it is already good as new. So there is, you cannot have anything better than that. Right? That makes sense. So if you have a new machine, of course, it doesn't mean to really overhaul that. But if it is already in state 1, which corresponds to actually to the state that the machine is operable with minor deterioration, right? Very minor, perhaps there is this overhaul is not economically sensible. In that case, we don't also get the benefit of spending this much of money, so we also just avoid really giving an overhaul to a machine which is in state 1. So these are now out of questions. Okay, but in state 2, overhauling the machine can really make a difference. Okay, in state 2, okay, an overhaul will then bring the machine to the better state, namely state 1. It doesn't make it good as new, but it makes it better than state 2, right? Namely, we can just move it to state 1, right? Okay, what are the costs involved, other costs involved with this operation? So we know that we have to pay 2,000, and unfortunately, overhauling the machine also takes a week. Remember, replacing the machine also required actually a week. So for a week, you just have to stop the production and just replace the machine. And this also happens with overhauling a machine. Okay, if overhauling a machine takes a week, therefore we will lose the production and the profits associated with that 1 week of production, during which you will have to overhaul the machine, right? So it takes a week, right? So, right, overhauling also costs, right, $2,000 of 1 week production loss. Okay. All right. So these are all the possibilities, right? We can take some of these actions if we find them favorable in some actions, and we may just take other actions in other states, right? So the possible decisions in different states then become like what? Okay. Right. First, let us also give names to these things rather than referring each time that I replace or we decide to replace or overhaul or do nothing. Right? Let us give just numbers so that we can work easily with this. So let's say 1 stands for the action do nothing. If you decide to not to take any actions, just leave the machine as it is, right? So that will correspond to taking action 1, 2 corresponds to overhauling the machine, and 3 corresponds to replacing the machine, right? Not all of these actions or the decisions available in each state. These decisions, right, are available only in the following states. Do nothing, right? If it is in good shape or with minor deterioration or with major deterioration. You can just, it is fine if you just leave it as it is, right? If it is in state 3, then we have to replace it. So we have to take an action because we have to produce, right? And overhauling, we just noticed it, right? In 0 and 1, it is ineffective. In state 3, it doesn't do any good. It is only available in state 2, right? If you take action 2 in state 2, then the machine is going to move to state 1. We know that. And if it is in state, well, decision 3 replacing it, well, that's available as long as the machine is not brand new. You will never replace a brand new machine right after you get that. So then we also have what? Costs associated with each of these decisions in each of these states. They depend both the state and the decisions, right? And what are they? So it depends. So let me just break down the costs so that you have you can visualize what's going on. So decisions. All right, then we have these decisions taken in different states, and the costs will depend on both of them. For example, the production, right, cost due to defective items, right? This is one cost item, and the other one is the maintenance cost. You know that when you decide to replace, then you have to pay for the new machine. When you decide to overhaul, then there is also a fixed cost, $2,000, right? This is going to be accounted in this column, right? Maintenance cost, right? And then we also have what? The cost of lost production. If you don't decide not to do anything, okay, the production will just resume as long as machine is in working condition. So this is going to be 0. But if you decide to overhaul the machine or replace, then you know that you have to stop the production for a week. There you will lose production. That the cost that we also have to take into account. Of course, we will just sum all these 3 cost items to find the total cost of taking the corresponding action in the corresponding state. Okay? So I'm still formulating the problem, right? We have to just bring all these qualities. So when you walk in a firm, of course, they are not, if they haven't done such a study earlier, they will just tell you all these things. It is your task to just to formulate the problem. What is it? What actions are available? What are the states? In which state? What action can I take? And what are the consequences, right? There are 3 consequences, and each of them will contribute to cost, and then finally we have to figure out what they are. The first decision, namely, right, decision 1, namely you don't take any action, right? So you can take this action according to this in state 0 or 1 or 2, and consequences of taking the same action in these 3 different states will be different, right? How is that? So if the machine is in good shape, so, well, you don't pay for defective costs because it is producing perfect items, no maintenance costs, you don't take any action, you don't stop the production, so you don't really lose any profits, so the total cost is going to be 0 in this case. In state 1, now you know that your machine is not perfect, it has minor deterioration, therefore it is going to produce defective costs, and it produces costs weekly defective items worth $1,000, right? So in $1,000, let us say, and I don't want to put a lot of zeros. Or should I? This is better. Maintenance cost, you don't do anything, so no maintenance cost. Actually, you have no maintenance cost for any one of these states. We know that, right? The production cost, lost production cost, since you don't do any maintenance, these are also 0, right? But now in this row, you have only 1 there, the sum is going to be 1. And if it is in state 2, again, the only cost relevant to this calculation is the cost due to lost production because of the defective items. There's the defective items, maybe. Production cost due to defective items. Okay? So this was 3. Since I studied this problem a few times, I remember the numbers. But otherwise, you're supposed to look at those statements. Okay? And the sum is going to be 3 as well. Right? So, other action that we can take is 2. And namely, you can overhaul the machine. But you can take that action only in state 2. Right? And if you decide to take action 2 in state 2, defective items Well, in this case, you are actually maintaining, you are about to overhaul, you already stopped the production, there is no production. So zero defective, zero production cost due to defective items because the production is not going forward. Maintenance cost, you have to pay $2,000 fixed in order to just work on the machine, just supply, replace parts of the machine, not the machine itself. And the cost of production, due to loss of production, right? Since you stop the production, and since overhauling the machine takes 1 week, you lose 1 week worth of production or the associated profits, which is $2,000, right? So we sum all these 3 components, you get 4. So yeah, now overhauling the machine, which is in state 2, right, costs $4,000. And okay, and then also there is the third possible action, right? Decision 3. You can take that decision as long as the machine is not good as new, right? If it is imperfect, inoperable, operable, or operable with minor or major deterioration, you can still take this action. But the consequences are going to be all the same for all these 3 actions, as we will just see now, right? So since you decide to replace the machine, there is no production going on, therefore there are no defective items to account for. The cost because of defective items equals 0. Maintenance cost in this case corresponds to cost of replacing or buying a new machine, which is $4,000. And since replacement also takes 2 weeks, or 1 week, also takes 1 week, right? So you lose the profits of 1 week production, which was $2,000, right? So we sum all these 3 quantities, right, to find the total cost, which is 6, right? So this is in dollar or $1,000, okay? All of them in per. Okay, so you should just, not allow me to erase this part of the board, I guess. Now we will need these things, otherwise we will have to produce them. Okay, now, right, now the main question is what? So we just summarize all the information given to us. The question is, what is the optimal maintenance policy, in the sense that can you find a maintenance policy with the smallest long-run expected average maintenance cost per time unit? Right? It is not immediately clear what the alternatives are, but in principle, right, we can take any one of these allowable actions, allowable decisions, or make allowable decisions in any of these states. What is the best combination of decisions and states so that the long run, right? So that the long run, right? Maybe I should just write that. What is the best combination of decisions and states, right? With the smallest long-run expected average cost per week. So maybe we should just give up saying all the time per unit time, because we now know in this problem the unit time is the week. So we would like to minimize the average cost per week. Okay? All right. Okay, it's, I guess, a good time to give a 10-minute break. So then we'll come back, and then first I'll describe how in general you can formulate a problem. Before we go back to our original problem, we'll discuss for general formulation of Markov decision process, and then we'll apply the results or what we understood from our discussion to this particular problem. Okay.